Greetings and welcome to a new video about another electric circuit example. In this video we will discuss the third example about the node voltage method, and in this particular example we will see also a current source and a voltage source in our circuit. This is a similar circuit we have discussed in the mesh current method, and now we will do it in a different form using the node voltage method. Well, of course, we'll look at the calculation step by step and verify our calculations in simulations using SPICE. So let's look at our example. We have the following circuit. You can see that we have one current source of 2 amps, it's shown here, and one voltage source Vm of 10 volts. And we have 4 resistors, 20 ohms here, 40 ohms here, 80 ohms there, and also R4 as 100. Now we need to use node voltage method to calculate the current through each resistor, so 4 currents, and also the voltage across each resistor, so we also need the voltages there. So in total we need 4 here, 4 there for this example. Now the current orientation we need to first define, so I have defined for myself the plus and the minus sign for the R1 here, that current goes then in that direction from left to right. For R2 I have defined my polarities as shown, and that current goes like that. And for R3 the plus and the minus also shown here, so the current goes always from plus to minus. And for R4 also same business, so the I4 is going in that direction from left to right. This is again just a choice you can make at the beginning. You can also take another choice, but your end result will be exact same if you have another, let's say, choice for your current orientation. Okay, now let's look at our solutions. For step 1 we determine the nodes in our circuit. So how many nodes do we have? We have the reference nodes, and that is always 0, so that is not new information. We have this node, that is definitely a new information, we don't know the voltage there. We also have this node. We also don't know the voltage there, so we have 2 nodes actually to denote here in the circuit. And there's also a node there, but we know what the voltage there is. That's Vm, which is 10 volts, so that is not really a necessary node to designate here. So you only pick the nodes where you don't know the voltages yet. So we have only 2 nodes, so we can name them as A and B, or X and Y, whichever you prefer. So we can just name them, and I just picked, in this case, A and B as the names for the nodes. Now the step 2 is write the equations for using the Kirchhoff current law for each node. Now for node A, I can now say, okay, I have a current entering, IS, in this node, and then 2 currents will leave from node A, which is then I1 and I4. That means IS will produce I1 and I4. That means actually the following. IS is then equal to I1 plus I4. Just mathematically this expression. Now for node B, I can see that I1 is entering and I2 and I3 are leaving. That means I1 is actually producing I2 and I3. That means the following. I1 is equal to I2 plus I3. Alright, now we have set up our, let's say, general expressions in step 2. Let's go to step 3 and then use Ohm's law to express these expressions, the current expressions, in terms of voltages and resistors. Why do we need that? Because we like to know the voltages at these nodes, 2 nodes. In order to do that, we need to express these in voltages, and also the resistors, because we know the resistor values, so we can come closer to the final, let's say, answers we require. So we use Ohm's law for each node. At node A, I look at my equation. It's IS is equal to I1 plus I4. IS is just a current, and I can just pick it from the given values. So I need to only write down I1 and I4 using Ohm's law, and current is equal to volts divided by the resistance. So that is then V1 over R1 for I1 and V4 over R4 for I4. Now what is V1 and V4? Now let's also check that. V1 is this voltage. So going from left to right, it means actually VA minus VB. That's actually shown here. So this is again the potential difference for each element. Divided by its resistance value will get you the current I1. In a similar form for R4 is this potential. So at this node, between this node and that node, from this left to right, and the right side you have the VM. On the left side you have VA, so it is VA minus VM. That is the voltage across the R4 divided by its resistance value will give you the I4. Now let's then substitute the values. We have 2 amps already given. VA minus VB we don't know. It is over 20 because the R1 was 20 ohms. VA we don't know yet, and minus 10 because the VM was 10 volts. That is then R4, that was 100, so we can also substitute that in the expression. Now we have an equation, we have 2 unknowns still, VA and VB. Now let's then continue and then get rid of these fractions. Now in this case I can use 100 as the multiplication factor from left to the right side, so I can say this times 100, this and this also times 100, so we will get 200. Now you will get 100 over 20 will be then 5 times this, as in between a parenthesis of course. And you will get only VA minus 10 here, because 100 over 100 is 1. So now work out these parentheses, collect the, let's say, the variables together and also the constants. I get 5 times VA minus 5 times VB, and also another VA here and minus 10. In total I get 6 times VA minus 5 times VB, and the minus 10 goes to the left side, will be then 210. And I then actually flip the equation. I'll get 6 times VA minus 5 times VB is equal to 210. And that is down equation number 1 for this node. Okay. Of course, we need another equation because we have 2 unknowns, so we need to set up the equation also for node B. Now, looking at the node B equation, we have I1, I2, and I3, so we can again use Ohm's law for each current equation, V1 over R1, V2 over R2, and V3 over R3. So similarly, what we have done here. What is V1? We already know that actually here, so with V1 is VA minus VB, and again, the resistance value, you divide that by, and then you will get your I1. V2 is this voltage, that's just the VB. Over R2, that will give you the current I2. And I3 is VB minus this node, which is VM. It's defined by this VM. And that is the voltage across R3. Over R3 will you get, then you get your I3. Now let's substitute now the values we have given. VA minus VB still unknown, over 20, R1. R2 was 40 from the information, and also the R3 was 80, and we have VM still. So we have now again another equation with 2 unknowns. We also like to get rid of this fraction, so let me then use a handy number scaling factor to get rid of this fraction. The 80 is, I think, nice number here to work out this in a nice form. So 80 times the left side and also the 80 times the right hand side, you will get 4 times this numerator, and you get 2 times the VB and just VB minus 10. That's shown here. Now work out the parentheses, you will get 4 times VA minus 4 times VB is equal to 3 times VB minus 10. Now you need to again collect the variables, VAs and VBs, on one side of the equation, and also the, let's say, the numbers or the constant on the other side of the equation. So I can get rid of this one and place it here and make that minus 7 VB, and this is then still 4 times VA. So 4 times VA minus 7 times VB is equal to minus 10. And I call this now equation number 2. So we have now developed, set up our 2 equations for this circuit. One thing to note here is because we actually have 3 nodes, but still have actually only 2 equations to work out here. That's due to this current source, and that is actually nice to see here. And also this voltage source already defines actually this node voltage here. So that is actually the main reason to have only two equations. If this was, for example, also a current source, then we have three equations, and I also need to assign here another node C, and I get three equations, three unknowns. A little bit complicated and also a little bit lengthy analysis, but still doable. Okay, set of equations to solve are these two. So we have this equation number 1 and also equation number 2. So let's bring them together and then move on. Now, actually, and using this, step 4 is actually calculate the node voltages A and B. Using this, what can we do? We can recognize here the following. We can say, okay, let's make VA's the coefficients equal, or for VB the coefficients equal, and then add them up or subtract from each other and then eliminate one of the unknowns. So that's actually always, let's say, the steps we use for two equations and two unknowns. So I can now select VA or VB to eliminate. I will take VA. What I do is the following. I say, okay, I will multiply this by 4 and this by 6. You can also say, you can better do this times 2 and this times 3. That's also fine, just a choice. So I do this 4 times, first equation. So we'll give you then 24 times VA minus 20 VB is equal to 840, 4 times each element. This will be then 6 times, will be then 24 VA minus 42 VB is equal to minus 60. Now, in order to get rid of this VA, I need to subtract as follows. First equation minus the second equation. Now you will get then this operation. This will be 0. So 0 times VA. And you will get now minus 20 VB minus 42. That will be then plus 42 VB. So we'll get 22 VB. And you will get now 840 I mean, minus 60 will get you plus 900. Now, in order to get a VB, you need to divide the 900 by 22, and that will give you approximately 40.91 volts. Okay, now we know this voltage at this node. Now, since I know this VB now, I can use this equation or that equation to calculate the VA. So we can now calculate VA, and I use this equation. You can also use this, no problem. So I can now use this equation and substitute in here 40.91. Now let's express this first, the VA, in terms of VB. So let's do that. That's actually minus 10 plus 7 times the VB, and that over 4. That is the complete expression for VA in terms of VB. Now let's then use this expression, or you can also use the exact value in here, and then you will get 69.09 volts. That is actually, let's say, the approximate value for VA. Now we have the VA and VB, and we can now move on to calculate the currents and also the voltages for this circuit. Let's do first the current. So we know the VA and VB, so we can say I1 was V1 over R1, and V1 was this voltage VA minus VB, and we know both of them, and we also know the current, so let's substitute the values and you will get 1.41 amps. Now for I2 you will get V2 over R2. V2 is just VB, and VB we know is 40.91 over 40, and you will get 1.02 amps. I3 is V3 over R3. So this one, VB we need, and we also need VM, because VB minus VB, it will be the voltage drop across this resistor R3 divided by R3 itself, which is 80. So you will get now 0.386 or 386 milliamps. Now the final one, I4, is V4 over R4. V4 is actually this voltage minus that voltage. That is the voltage drop across R4. Now let's also substitute the values VA and also the 10 over 100, which is the R4. Then you will get 0.591 amps or 591 milliamps. Now we have the answers for question A. Moving on to question B, which is the voltage across each resistor. That is really straightforward. We already did that actually in our analysis in question B, A, I mean. So V1 is just this voltage, VA minus VB, and that is already calculated 28.18. V2 is just VB, that is then 40.91, and V3 is VB minus VM, that is also straightforward, just this value minus 10, 30.91. And V4 is VA minus VM, that is also really straightforward, 59.09 volts. So we have everything from the calculations using these two values, VA and VB, that are the node voltages. Okay, moving on and have a summary. This is all the summary of the results. This is what we have gained or got from our node voltages, and these are the results. Now let's also look at the simulation. This is the circuit I have drawn and developed drawing in the simulator, and these are the results when I do the DC analysis for the voltages and the currents. You see several values here. Let me just make a box around this part. These are all the currents in red. And these are the currents we have calculated. So I1 here in the calculation is 1.41. If I look at this, I underscore R1 is 1.409 amps. So very close to what we have calculated. Looking at I2 is 1.02 amps. And it's also very close to 1.02 amps for I2. You can also see the labels here. It is actually saying 3,0 means actually from 3, label 3 here, up to the 0. And in a similar form you can do that for I3, 386 milliamps. It's also shown here, very close to that one. That small difference is actually due to the rounding off errors. If I use exact values, I get much closer to this. And also I4, which is 491 milliamps, also very close to what's shown here in the simulation. Now the voltages, these are the voltages across each element, R1, R2, R3 and R4, all shown here, and these are also very close to what we have calculated. So you can see it, they really match actually our calculations. So nice to see actually that the calculations are verified using the simulation results shown here. Now what we now do is we will jump now to the simulator in TNT Spice and show you actually this circuit again, and how you can generate this, and then show you something and also give you a briefly discussion about the circuit. So let's jump to the simulation in TNT Spice. Alright, we are now here at the screen of TNT Spice simulator. This is a circuit we have discussed in our calculations and also show you the simulation results. Now we have the circuit in the actual simulator. So I can click on the components. You can see this is the VM, which is 10 volts, the DC voltage source, the IS, the DC current source, and also the 4 resistors. Now let's then generate that table. You can go to analysis and DC analysis and then make a table, or you can also look at it from the node voltages. Let's first look at the table. Click on this and you get the table. It is generated. Let me show you this, the complete picture next to each other here. Now if I now click on, for example, R1, I can see it's highlighted its current 1.409 amps, which is what we also very close to what we had, 1.41, and also 28.80 volts, very close to what we have calculated. You can also do that for R2 and R3 and R4. You can also see the node voltages. So if I click with my pen on this node, you can see 40.91 volts, which is actually VB, what we also have calculated. If I click on this one, you can see 69.09 volts, very close to what we have calculated also. Now this node is of course just 10, so that is already defined. So you can see that you have actually the values also from the simulated in this form. You can also do another form. You can say DC analysis and calculate node voltages. Then you get specifically for each resistor the current and the voltage and the current directly. So if you prefer that, you can just look at this in this form. So you can also show here, this is the, or you can do it like that. But now you see that the arrow is going up. That means, well, that's why you have a minus sign here. Alright, this is now the discussion also in the simulator for this example number 3 using the node voltage method for the DC electric circuit. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share this video so that we can reach more people for this interesting topic. Thanks for your cooperation and see you next time in another interesting video. Take care.